this example I just show you max heap. What does it look like? Max heap. Yeah. So let me show you this example again. We store a near complete binary tree in an array. Yeah. So what do you see in an array like this? But actually the structure is like this. Okay? Yeah. So these two objects, one-to-one correspondence. Yeah. All right. And max heap property, the value of every parent node is greater or equal to the values of its child nodes. Two possible. Yeah. Up to 2 child nodes. Yeah. Some of the nodes, so look at this node, only 1 child node, right? Yeah, 1 child. And look at these nodes, no child nodes, okay? Yeah, no child nodes. Later, we will call them leaf nodes, leaf, tree, because you have a tree. Tree has many leaves, right? Leaf nodes, yeah. So we have that concept, yeah. All right, so we will get there, yeah. Yeah, so here, the parent-child relationship, right? The definition, yeah. So I do not repeat it again, yeah. Next, let's continue our discussion. Maintaining the heap property, yeah. Remember, we use this heap to manage our dynamic data. Yeah, so the data items come in and get out, dynamic data. So we need to consider insertion and deletion. Yeah, insertion and deletion issue, right? Yeah. Where a new data item is inserted, our original max heap property could be violated somewhere in the tree. Yeah. There could be some violation regarding our max heap property. So at this point, we need to talk about how to maintain the heap property. If you detect there is some violation, then you need to fix it. So how to do it? So we want some relatively fast way to fix any violation. Yeah. So let's look at that. Yeah. Due to some operation. Yeah. So when you do insertion or deletion, yeah. So definitely you cannot guarantee the whole max heap, the max heap property for the whole tree still maintain, still there. Yeah. So we need to consider possible violation. Yeah. So let's consider this 3-node local triangle. Yeah. So this is a representative part of a local region in this max heap binary tree. Yeah. PLR, 3 nodes. We need to check it for the max heap property. Yeah. All right. Yeah. In this local region, 3-node triangle, this local region, yeah. Now we want to compare values among parent-child nodes. Yeah. All right. And at this point, we can assume, left subtree, right subtree, both max heap. Yeah, so both valid max heap. We only consider the local part. Yeah, so we do not need to worry about, global, the whole tree. Yeah. Because if we can fix the local region, then we can fix everywhere. Yeah. So this is a representative, typical discussion. Yeah. All right. Local fixing operations. Yeah. Yeah, because after we can do the local fixing operation, then we can apply the same operation everywhere in the whole tree. Yeah. But you need to follow certain order. Yeah. Certain order. Okay. Yeah. Yeah. You know, scanning the whole tree in certain order. Yeah. All right. So let's look at this we call the local heapify operation. Heapify. Yeah. Recover the heap. Yeah. 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 Because recover actually the max heap. Yeah. Max heap. Yeah. Min heap. Yeah. We just change the direction. Yeah. We can get a min heapify operation. Yeah. Yeah. But to save some time, we only focus on the max heap. Yeah. Recursion approach. Yeah. Yeah. Because we can, taking the recursion way. Yeah. So you start somewhere, then do recursion. Yeah. All right. But we need to work on the local triangle here. Yeah. P. Yeah. All right. So here I put a pseudocode here. Yeah. How to check the heap property violation. Yeah. First, let's check this inequality. If A of I less than A of 2i, so we compare the value of the parent node and the value of the left child node, 2i. A of 2i, left child node. Yeah. If yes, then it's a violation, right? Yeah. If yes, yeah. Violation to our max heap property. Yeah. Because based on the max heap property, A of I should be greater or equal to A of 2i. Yeah. Here, the first violation detected. Then we store the index of the left child, 2i. Store the index of left 2 child to a temporary variable we call the largest. Yeah. This largest temporary variable to store the largest possible value among the 3 nodes. That's our goal. Because based on the max heap property, the largest value should appear in the parent node, P node. Yeah. Not L node, not R node. Here we need to do that. Yeah.
According to which property?
Max heap property. Max heap property. Yeah. Yeah. So here I do not repeat. Yeah. The details. Yeah. All right. Yeah. So that's the first violation. Yeah. This temporary variable hold that index, 2i index. All right. Then we need to check for the second violation. Else that means no violation, right? Yeah, else means no violation. If no violation, then the index of the parent node, I, should be in the largest temporary variable. Yeah, no violation. Okay, all right. Then the second violation, we compare A of largest. Yeah, A of largest this time. Yeah, because this variable, temporary variable, should hold the index of the larger one, the previous larger one. Larger one in parent node and left child node. Yeah. Index of points, the index points to the larger value in parent node and the left child node. Yeah. So then, if that value, A of largest less than A of 2i plus 1, right child value, the second violation, the second possible violation. Okay? Yeah. second possible violation. Yeah. Then we should update this largest temporary variable. Yeah, so we replace it by 2i plus 1. 2i plus 1, right? Yeah, after these 2 rounds checking, so we cover these 2 possible violations. Now, we need to fix it. Yeah. So this is a detection step. Detection step, we need to check 2 possible violations. Okay, I check for 2 possible violations. Then, next, fixing step. Yeah. Fix the violation. Yeah. All right, how to fix? Yeah, very easy. Yeah. All right. Now, before we fix, we need to check if the value in this largest variable equals parent index I or not. If equals parent index, that means no violation, right? Yeah. After 2 rounds checking, the largest variable still equals the index of the parent node, that means no violation. If no violation, we do not need to do fix, right? Yeah. So no fix needed if there is no violation. That otherwise, oh sorry, yeah, not equal, yeah, here, yeah, all right. Not equal, then there is a violation. If equals, no violation. So if equals, then, we complete, right? If equals, we get out of this function. But if not equal, there is some violation, we do a swap operation. Swap, what kind of swap? Swap A of largest and A of I. Yeah. After this swap operation, then we fix the max heap violation locally, yeah, in a local triangle. Yeah. Then you can do this operation everywhere, following certain order in the whole heap. Then you can recover max heap again. Yeah. After any insertion, deletion operation, then you need to run this to, recover the max heap again. Okay, so that's the way we handle the dynamic data. Yeah. All right, yeah. So let's move to 8.4, heap example. Yeah. Show you how to use a concrete example to show you how to fix, any violation problem. Yeah. All right, so here, let me show you a simple example. Max heapify example. Here, that gray node, that's the place you can detect a possible violation. Yeah, because look at this local triangle. Okay, 3-node triangle. Yeah. And you can easily see the max heap probably is violated. The value of parent node 4 is less than the value of any of its two child nodes. Yeah. All right. Then we need to fix it. Okay. So we need to run our previous max heapify operation locally. Yeah. Here locally. All right. Yeah. Yeah. Here we use our eyes. We can, which swap operation? Yeah. So after 2 round checking, at a fixed step, you need to do swap between these 2 nodes. Okay. Yeah. Value of the parent node and the value of the left child node. Then you do a 1 swap operation. Right? Yeah. After 1 swap operation, yeah, that gray node moves down level in the tree, binary tree, moves down by one level down. Yeah. But that gray level, we still mark it gray. Yeah. Why we still mark it gray? Because there is still possible violation. Okay? Yeah. So that gray node still, it may carry some possible violation with that node down the road. Yeah. Down the road. Yeah. So we need to run another local triangle checking fixing. Okay? Yeah. And you detect another violation, right? Yeah. So you need another swap between these two nodes to fix it. Yeah. So after another swap, yeah, because that gray node reaches the bottom level, yeah, hit the ground, right? Yeah. Because after that, this node, there is no child node. Yeah. It hit the ground. Yeah. All right? Yeah.
It goes from left to right, right?
Yeah. Left, right, it doesn't matter. Yeah, because our checking step, we compare both, right? Left, right. Sometimes going left, sometimes going right.
So we're only looking for the largest to get, for the parent node?
Yeah, so here we assume this node, there is a violation that occurs at that node. Yeah, so we start from there.
So like the third child node, 1,
Yeah,
is that in the correct order?
you mean this one?
Yeah.
You're talking about this one?
Yeah.
We didn't touch it. Okay.
Those were not.
Yes. Yeah.
Okay.
Yeah. So here, all right, we only do the operation, fixing operation that may be touched by this node. Okay, impacted by that node. Yeah.
Thank you.
Yeah. So for other node, so we assume no problem. Okay. So here we only fix a local violation. So this is a local violation fixing example. Yeah. Yeah. So when that gray node reaches the bottom, the very bottom of the heap, yeah, the ground level, okay, the ground level, then the problem is gone, right? Because when it reaches the bottom, that means you are 100% sure there is no violation, right? Yeah, because no child. If there is no child, that means no violation, right? Yeah. So we make it white. Yeah. So we change its color to white. Okay? Yeah. So that means this node becomes clean. Yeah. It's a clean node. Yeah. The gray one is a dirty node. Dirty. So some problem, yeah, potential problem, violation. So it's dirty node. Yeah. So we need to keep track of the dirty node all the way down to the bottom. Yeah. Down somewhere. Yeah. Yeah. All right. Yeah. So from this example, so you can understand the max heapify operation. Yeah. How do we do it? How do we run this operation to fix a local violation? All right. Yeah. Now next. Yeah. Next, then we need to gradually move toward a heap sort. Yeah. Our goal is heap sort. Right? Yeah. Sorting. Yeah. Heap sort. Yeah. So we need to move toward that goal. Yeah. So the next step toward that goal, building a heap. Yeah. Part 1. Building a, so given an array, given a random array, yeah, the values in the array randomly distributed. Yeah. So we do not have any idea. Yeah. But we need to start, build. So we need to make it a max heap. Why we want to make it a max heap? Because we want to run heap sort. Only when we have a max heap object, then we can run the heap sort easily. Yeah. So here you can see we spend a lot of resource to make it a max heap object. After that, then running heap sort, very easy. Yeah. Very easy. Yeah. So you will see it. Yeah. All right, so let's do this building example. Yeah. So the given array is like this. Okay? Yeah. Yeah. You know, a random simple array here. Yeah. First, before we make it a max heap, let us just arrange the elements following the natural order to, to place these values in a near complete binary tree. So here it's a near complete binary tree, right? Definitely it's not a max heap. Okay? At the beginning, it is not a max heap. Yeah. But at the end, we want to get a max heap. Okay? After we run that max heapify operation in some special way, at the end, we want to see a max heap object. Okay? All right. Here, I want to show you how to run max heapify operation in the right order to make it a max heap object. When we start, we need to scan this whole binary tree following certain order. So what's the order? This order, bottom up order. Okay? Bottom up. In each level, from right to left. Okay? From right to left. Yeah. Then, if you look at the levels, bottom up. Okay? From bottom, one level by level, toward the top. All right. So when we start, first, let us check the last local triangle. Is there any violation? No violation, right? No violation, we move to the next one. Okay? Next local triangle. Is there a violation? Yeah. So I put a star, that means there is a violation. So we detect, okay? We detect, so we found a violation. Yeah? Star. So let's run local heapify operation. Okay? Max heapify operation. After you run max heapify operation, you need to swap these two nodes, right? Yeah. You need to swap these two nodes based on our max heapify operation. After the swap, then we move to next local triangle and we detect another violation. So we put a star there. You need to do that max heapify operation, and to fix it, swap these two nodes to fix the violation. Yeah. So after that, you move to the next, because you follow the order, right? Bottom up and from right to left. Okay. Yeah. Following that order. Yeah. Then to fix it, you need to, because the larger one, right? Yeah, the larger one, yeah. But after you swap these two nodes, you move that dirty node one level down. Node containing value 1, do you need another swap to fix it, right? Yeah, because it carries a violation, right? That dirty node still carries the violation. Still dirty, still not clean, right? So you need to do another fixing operation down the road, all right? Yeah. So after that, when you reach the bottom, then it becomes clean, okay? It becomes clean. Yeah. All right, after that, then the last local triangle to be fixed. This one, yeah? So another swap operation between these two nodes. Then down the road, right, all the way down to the, you need to, keep track of it.
So we go from right to left, right?
Yeah, right. Yeah.
So do we switch 10 and 4 and then switch 16 and 10?
Right.
That,
6 and 10? Sorry, which step?
so we're going from right
Right to left, right.
So are we switching 10 and 4 and then 10 and 16?
No.
Taking the whole thing.
Go back to our, how do we make our max heap file operation? Yeah. 10 and 16, we only switch with the larger one, right? We don't touch the smaller one. Yeah. When you swap the parent node with the one with the larger value, the bottom two. You do the larger one, okay?
Larger one among the whole.
Yeah, a whole triangle. Okay, whole triangle. Yeah, so that's recall our max heap file operation. Okay, yeah, two-run checking. Remember, the largest temporary variable, that variable holds the index containing the largest value among the triangle. Okay, 3 nodes in the triangle, the largest. Yeah, that's the meaning of that largest, right? Yeah. All right. Yeah. So the last local violation fixing operation here, but all the way down, right? That dirty node. So this is the last dirty node. But when we fix it, we need to do it all the way down. Yeah. The first swap, then the second swap, right? Then the third swap, right? Yeah. So we need to do, down the road, we need to do 3 swap operation, right? Yeah. Okay. Yeah. So here, yeah. So that's the, after the first swap operation, we get this one. After second and third, then when we get here, can you see? Yeah. Use your eyes to check if it is a max heap object or not. Max heap. No violation, right? If you look at the whole heap, there is no violation. Then we're done. So that's the process, building a heap process. We're done? Yeah. Okay? Yeah. Yeah. So we can write a program to do this, right? Given array. So we can, write it. You can use recursion to implement, Yeah. Yeah. Although recursion, can you use a for loop? Non-recursion way. No. Although we can use a recursion way, but if you can use a for loop to do it without recursion, remember, if you can avoid recursion, you can avoid the stack, right? Stack. For loop, you do not use a stack. Remember, if you use a stack, the stack could be deep, right? If the stack is deep, you use more memory resource, right? Yeah. So for this one, if you want to implement, building a heap, yeah, it's better to use the non-recursive way. Yeah. Use a for loop or while loop without stack. Yeah. Then you can save a lot of memory resource. Yeah. All right. Yeah. How to build a heap? But the question is, how much cost do you need to build a heap? Building a heap, there is a cost associated with that process, right? But how large is the cost? You want to know it, right? Yeah. If the cost is too expensive, then we may need to change our idea. Too expensive. So this method, we don't want to take it. Yeah. If the cost is too high. Yeah. For example, if the cost is big theta of n squared, we know regarding the heap sort, that's too bad. Too bad. So we don't want to take it. Okay? So our next step, we want to estimate the total cost for the heap building process. For the heap building process, what's the total cost? Okay? We want to see if that cost is acceptable or not. All right? Yeah. Good enough. If it's not too bad, then we can continue this idea. Okay? Yeah. All right? Yeah. But to estimate the cost, then we need to do a lot of work. Yeah. So the first step, we need to do the work, B.1, heap nodes in each level. We need to calculate the heap nodes in each level. Okay? Yeah. Yeah, but here, this level, the meaning of this level here. Yeah. So later in our discussion, you will see because the exact meaning of the level is pretty vague. Yeah. It's based on how do you define the level, right? Yeah. Because you have different ways to define the level. Yeah. So here, we will use a special way to define the level. Okay? Yeah. It's different from our natural level. Okay? Binary tree, you have that natural level, right? Here, we need to change that meaning slightly. Okay? Yeah. Slightly different from the natural level in a binary tree. Yeah. All right. So let's look at number of leaves in the heap. All right. Now, first we want to calculate. Given a heap, how many leaves you can find in a heap? So what's the leaves, right? Yeah. What's the leaves? Yeah. So when you have a heap, yeah, in this heap object, yeah, those nodes without any child, they are leaf nodes. All those nodes without any child, right? Yeah. So that's, we call it, ground level, right? So, yeah. Because below those nodes, no other nodes, okay? They are at the very bottom, okay? Very bottom, the lowest level. Yeah. So here you can see the binary tree natural level, these two groups of nodes, they are at different level, right? Yeah, different level. But if we use the ground, we count from ground, yeah? So this part higher ground, right? Yeah, still ground, but higher ground, right? So if we count from the very bottom, we treat these nodes, they are in the same level, counting from the ground level, okay? Ground level, we treat as level 0 level. Then move one level higher, level 1, level 2, and so on. Okay? Yeah. So we use a new way to talk about levels. Yeah. Yeah.
So what will be level 1 for that?
Level 1. All right. Yeah. So I will get there. Yeah. But at this point, level 1. All right? Yeah. One level higher. Okay? One level higher. Yeah. Actually, later I will introduce a height concept. Height concept. Yeah, level 0 means height 0. Level 1 means height 1. So here, height 1. Height 1. Here also height 1, right? Yeah. Height concept. Yeah. All right? Yeah. Describing leaf. So the nodes without children, then we called leaf nodes. Yeah. Now we want to count number of leaves. Given any heap, we want to calculate. We want to find a formula to give us the number of leaves in the heap. Yeah. To get that, now we need to study parent-child relationship. Yeah. So based on our definition, the parent node, here we use A of I, that's the parent node. the left child. Yeah. We have left child, we have right child, but this place we want to pick the left child. Yeah. Why? Because if a node has a child node, it must have a left child, right? It is not necessary a node with a child node, non-leaf node, it's not necessary it must have a right child, right? Yeah. Yeah. It's not necessary a non-leaf node must have a right child, right? But a non-leaf node must have a left child, right? Yeah. A non-leaf node must have, so this here, this is a non-leaf node. Non-leaf node. Non-leaf node, it has a left child node, but it does not have a right child, right? It does not have a right child node. Yeah. So that's the reason this place we pick the left child node. We want to study the parent-child relationship. Yeah. Left child is better than right child if we want to see if this node has a child or not. Okay? All right? Yeah. That's easy observation. Yeah. All right. Then, the relationship between these two nodes, 2i and i. 2i and I, that's the relationship between these two indices. All right, yeah, all right. Yeah. But we need to consider, given a node A of I, when we look at its possible left child node, A of 2i, we need to see, is this 2i number out of range or not? Because the array indices have a range, right? Array indices in the range between 0 and n-1, right? Array indices. Yeah. But if you double an array index, there is a possibility when you double it, then it may be out of the range, right? There is a possibility after you double it, that 2i is out of the range. If it is out of range, that means this node does not have a left child, right? That node, when you double its index, it's out of range. Then it cannot have a left child. If it cannot have a left child, then this node has no child, right? If this node has no child, that means this node must be a leaf, right? This node must be a leaf node, okay? Yeah. Then we find a description for a leaf node. How do you describe index of a node for a leaf node? Well, you double that index, it is out of the range, then this node must be a leaf node. That simple. Okay? Well, you double its value, index value, it is out of the range of the indices of the whole array. Oh, actually, to be more precise, should be 1, right? Because 0, we do not use that location, right? For a heap. We never use 0 location. Yeah, so we can use 1. Yeah, more precise. Yeah. All right. Now, we can use inequality to represent the meaning of no child. How to represent a node without any child? This is the representation. Yeah. First, yeah. All right. So here, actually, yeah, n-1. Yeah. So here we change because there are n nodes in an array, right? Here we modify the range between 1 and n. Yeah, because the total number of nodes we assume is n, right? Not, yeah. So here we use, upper bound of the range is n. Okay, yeah. We skip the 0 location, but we have total n nodes in a heap. Yeah, yeah. So we change that. So for that reason, I less than or equal to n. One side. The other side, 2i out of the range. 2i must be strictly greater than n. Out of the range. Yeah. So this is the description for a leaf node index I. Leaf node index I. Okay? Then we want to simplify this inequality. Yeah. Index range. Simplify. Yeah. So we get a n over 2 less than I. Yeah. 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 But we know I is an integer, right? Yeah. So we need an integer expression for I. Integer expression. Yeah. Yeah. All right. Because this is a strictly less. Yeah. It does not contain equal case. Does not contain equal case. Even if n is an even number, this is an integer, but I strictly greater than that number, so that's why we need to plus 1. Seeding function, floor, we use floor function and plus 1. That I is strictly greater than n over 2, no matter n is even number or odd number. Okay? No matter n is even or odd. Yeah. So we find the smallest such I. Yeah. What is the largest such I? Largest such I. That's easy, right? Easy to see. Largest such I, n. N is the largest such I. Okay? So then you find a range for I. This is the range for I. Okay? Floor function of n over 2 plus 1 as the lower bound and the n as the upper bound. Okay? Yeah. Now you tell me, how many elements, here we do counting, how many i's can you find within this range? How many i's? Do counting. Which number minus which number? You need to do subtraction of two numbers. I gave you the method before. Yeah, long time ago, I give you one method to count number of elements in a given range. All right. Use the upper bound, and minus the number right before the lower bound. Not lower bound. Do not, if you minus the lower bound, then one difference. Yeah. So you minus the number one less than the lower bound. Okay? One less than the lower bound. That's the floor function of n over 2. So n minus floor function of n over 2. That's the total number of i's in this range. Answer, n minus floor function of n over 2. That's the counting. Okay? Counting a number of elements in a given range, including two boundary points. Okay? The two boundary points, here you have equal signs, so including two boundary endpoints. Yeah.
When n minus n by 2, just be n by 2.
N by 2, yeah. Floor function. Yeah. Integer division. Integer division. We drop the fractional part. Integer division. Yeah. Yeah. Because here we cover both even and odd, right? Yeah. We want to take integer expressions. Yeah. Yeah. All right. Yeah. So here, this is the expression, number of leaves, right? So the formula for number of leaves, this is the formula. All right. But there is another equivalent formula. Same value, but in different expression, there is another one. That is the seeding function of n/2. Seeding function. Here, be careful. Look at the one flow function, one seeding function. Notation, different. Yeah. So this formula, we use this formula. It's in page 477 on our textbook. Yeah. Appendix. We have some formulas. Yeah. So here we use this formula given in the appendix of our textbook. Okay? All right. Yeah. So here we can simplify a little bit. Yeah. All right. Yeah. But these two formulas, sometimes one is better than the other. Yeah. One is better than the other. Yeah. All right. So we complete this one. That's the number of leaves. Next, we need to move one level higher. All right. So number of internal nodes with height 1. Yeah. First, what's the internal node? Second, height 1. Height concept. Yeah. We need to define height concept. Yeah. All right. Yeah. First, look at this example. Yeah. Now you know the leaf nodes, right? Yeah. So given a binary tree, other than the leaf nodes, the remaining nodes are internal nodes. Okay? Yeah. Leaf nodes, people also call external nodes. External. Okay? Leaf nodes, the same thing. Yeah. Then the complementary part of the internal of the leaf nodes. Complementary part, internal nodes. That's the internal. Then height 1. Yeah. These nodes height 1. Yeah, because how do you see the height? Starting from this node, we follow a path, moves down to the bottom. How many edges do you need to reach the bottom? Okay, here, one edge. You go along the path, your path has one edge. You count the number of edges of the path. You can follow, reach the bottom, that number of edges. That number you define as the height number. Here, height number, you follow this path, reach bottom, 1. Okay? Yeah, 1. All right? Yeah. Yeah. All right. Yeah. Height 1. So here we want to count total number of nodes, internal nodes with height 1. Okay? All right. All right. First, how to count the number of internal nodes? Complementary part with respect to external nodes or leaf nodes. Leaf nodes, we know the leaf nodes, right? Number of leaf nodes. Yeah. Total nodes and number of leaves. We got that formula, number of leaves. All right? Yeah. Two formulas. Sometimes the first one is better. Sometimes the second one is better. This place, when we calculate the number of internal nodes, the first formula is better. Because the first formula, we can easily calculate the complementary part, right? The complementary, yeah. To calculate the complementary part of this one, yeah, the offset, right? That number, flow function of n/2. Flow function of n/2. That's the number of internal nodes. Okay? Yeah. Yeah. All right. But in the internal nodes, these nodes, they have different heights. Okay? They have different heights starting from 1. 1, 2, 3, going higher. Yeah. But we want to see how many of them have height 1. That formula. All right? Yeah. Number of internal nodes with higher. Yeah. Because if a node has height 1, then its child node must be a leaf node, right? It's a left child. Yeah, we look at its left child because that node may not have the right child, right? Like this one. This node, it has only left child. It does not have right child. Yeah. So let's look at its left child. Its left child must be a leaf. Must be a leaf. Okay? All right. Yeah. And 2i is the index of its left child. Okay? Index of its left child. Left child. Okay? All right? And 2i must fall in the range for a leaf node. Yeah. So this is the range for the leaf node, right? Yeah. But it's for the 2i. 2i. Yeah. But we want to see the range for I, not 2i, right? We want to see the range I. Yeah. Let's do division by 2. Division by 2. Okay? All right. Division by 2. Yeah. This side, easy. Yeah. Because I is integer, then we need to take the integer operation, so the floor function, right hand side. But this side, how to see this side? This side is not easy to see, left hand side. Yeah. To see that, actually the left hand side should be like this. It's easy to see the left hand side should be that expression, but that expression can be simplified to this one. Yeah. How to simplify it? How to simplify? We need to do discussion. We need to consider n mod 4, n mod 4. When n mod 4, there are 4 cases. The remainder is 0, 1, 2, 3. 4 cases. Then we use those 4 cases, we check this formula. Okay? Yeah. Yeah. So we can verify this formula. All right? Yeah. Yeah. So here I skipped that part, checking part. Yeah. So we can use this formula. All right? Yeah. Now, the range, now you know the range, right? Yeah. Then how to calculate the number of internal nodes with height 1? We use our, counting way, previous counting way, using the upper bound minus the number that is 1 less than the lower bound. 1 less than the lower bound here. Yeah, so this is the formula. Formula for the number of internals with height 1. Okay, all right, yeah. So we get this formula. All right. All right, but this formula, this time, there is another expression, but it's less than equal. Yeah. It's not equal, okay? Yeah, it's not equal. Yeah. You take the seeding function, yeah. This time not equal because when you use the 4 cases here, for some of the cases they are equal, for some of the cases they are not equal. So you should be careful. Yeah. So here it's a less than equal inequality. Yeah. All right. Then let's move to next step. This time we want to count the number of internals of any height. Any height, not just the one. So 1, 2, 3, 4. Any height. Here we use a variable h. H to represent the height number of any internal node. H. Yeah. All right. We generalize the previous result this time. Yeah. Number of leaves, because leaves, the height number is 0, right? Height is 0. Nodes. They are the leaf nodes. Yeah. And number of nodes with height 1. this range and the number in that way, can you see some rule? Yeah. There is some rule, right? There is some rule. Yeah. So the number of nodes with height h, you can get the range is like this. Okay? Yeah. Because here the height number, 2 to the first, right? So here, 2 to the first. Yeah. This 2 is 1 plus 1. The height number plus 1. So here for the general case, height number h plus 1. And upper bound, you use h. Okay? So that's the range. The counting number, the number of nodes with height h, the counting number, we use our same counting way, upper bound minus that number 1 less than the lower bound. Okay? Yeah. So that's this many, the formula given. Okay? Yeah. All right. Then later when I ask you, so if I tell you the number of nodes in a heap, I give you n number. I ask you how many nodes are there in this heap with height, for example, 3. Okay? H equals 3. Then you use this formula. Okay? Use this formula. Yeah. When n is certain number, I give you a concrete number for n. Okay? For example, 124, for example. Yeah. All right? Then h equals 3. Then you need to use this number. Yeah. But many students, when they answer this question before, yeah, they didn't look at the notes. So they didn't use this formula. What they do, all right, so they start with a binary tree. Okay? So they start with the binary tree. All right? Yeah, like this. From top to bottom. All right? And so on. Okay? From top to bottom. Then height 3. What's the height 3? They count, this is the height 3. It's not, right? That's not our definition of height, right? So they count. They come from root. So this is the root. When we define height, we come from bottom, right? When we count height, we come from bottom. Bottom is the 0 level. Then one level higher. Then those students, they count down from top, okay? They count down from top, height 1, height 2, height 3. That's wrong, right? Yeah. So many students, they treat the height concept counting from top. Yeah. Actually, counting from top, we have another concept we call it depth. Depth of the node. Okay? If you count from top, okay, that's the depth, not height. Okay? So different concept. Okay? All right. Yeah. All right. Then you see how much time I have. Yeah. About 10 minutes. Building cost of a heap. We need to estimate the building cost of the heap. Yeah. Combine the cost of all heights. If you know the number of internal nodes with given height, you can estimate the number of costs you do when you run max heapify operation for that level of nodes. Yeah. All right. Cost of max heapify for all nodes of height h. Because when you estimate that cost, you need to consider the worst case, right? Yeah. When you estimate the cost, you need to consider the worst case of the cost. Worst case, you move from that point, current point, all the way down to the bottom, right? That's the worst case. All the way down to the bottom, that's the worst case. Okay? All right. How many steps you move down? for a height h node, how many steps you move down to the bottom? H, exactly h. You know that h, that number, okay? Yeah, all right. But you have this many nodes, right? Yeah. Each node, you need to do constant multiple of h operations. Constant, yeah, here, we assume some constant, okay? Constant multiple, okay? All right, yeah. Each one, constant multiple h, yeah. But you have that many nodes. So your total cost multiplication, okay? Here we use big O, yeah, because we want to look at the upper bound. We do not need to worry about the lower bound, okay? When we estimate cost, we want to see what's the upper bound. So here we use that big O. Big O.
Oh, sorry, you mean like the worst case?
Yeah, yes, worst case, yeah. All right, yeah. So the heights from 1 to log base 2 of n, yeah. All right, yeah. So log base 2 of n, all right. Because leaves height 0, leaves we do not need to run max heapify operation. So we skip all the leaves. No max heapify operation for leaves. So we skip them. Yeah. All right. So that's why from 1 to through log base 2 of n. Flow function here. Okay. All right. Then the summation, we accumulate all the cost. Accumulate all the cost. Okay? Yeah? All right. Yeah. Yeah. Next question, how to estimate the summation. If we can estimate the summation, then we know the building cost of the whole heap. The building cost. Yeah. So this is the last step we use to estimate the building cost, heap building cost. All right. So let's do some simplification. Yeah. Yeah. Because when we do estimate, we can enlarge the expression slightly to make the expression simpler. Yeah. Because here we use the ceiling function. We know ceiling function is not very easy to handle. So we want to remove the ceiling function. To remove, we use its slightly larger upper bound expression. Yeah. When you plus n over 2 to the h plus 1, you get a slightly larger expression, but without ceiling function. We remove the ceiling function. Yeah. All right. But you have a plus 1 here. Okay. You have plus 1 here. Yeah. All right. Then plus 1 we split, okay? Because there are two terms, the first term, second term. The first term, we do the first summation. Second term, we do the second summation, okay? So there are two summations we need to calculate. Yeah. But the second summation is easy. So we do the second summation first. Easy, all right? Yeah, yeah, yeah. This big O, it may not be a good. So when you do the calculation, you can consider constant C times H. That's easy calculation. Yeah. Constant C, upper bound. Upper bound is, there is some constant C. Okay, all right. Yeah. Yeah. So then, yeah, because the summation, you add consecutive integers from 1 through certain number. Here the number is log base 2 of n. So this is the estimate. All right? Estimate approximately, so log base 2 of n squared. Log base 2 of n squared. So that's the second summation. Okay? Second summation. Yeah. The hardest part, main term, the first summation. We need to calculate the first summation. Okay? First summation, because this n, during the summation, it does not change. Okay? Only h value changes. N never changes, so you can factor this n out of the summation. Factor that n out of the summation. Yeah. During the summation, n never changes. All right? N never changes during the summation. So you can factor it out. Yeah. H keeps changing. Yeah. All right. But this upper limit, log of base 2 of n, floor function, is quite annoying, right? Because that expression, hard to control. So that one is quite annoying. Yeah. So we want to remove that log base 2 of n. Remove it. Yeah. How to remove it? We enlarge it. Okay? Enlarge it. Enlarge to what? To infinity. To infinity. We change it to infinity, then this whole summation becomes larger, right? Whole summation becomes larger. So we are very generous to enlarge. Okay? We are very generous to make it larger. Yeah. So we replace that upper limit. Yeah. So here we ignore this n. Okay. We only look at the summation part. We change the upper limit to infinity. We are very generous. Yeah. Even if we are very generous, this summation can still be bounded by some constant number. That is good. Constant number. That's all we need, right? Certain constant number. Yeah. Next, let me use a few minutes to calculate this constant number. All right. So here you can see, basically we are doing a summation of this sequence. This sequence summation. All right. How to calculate the summation of the sequence? Yeah. Yeah. So there is some little trick we can use. Yeah. Some little technique we can use to calculate this summation. Yeah. So let's do it quickly, then we finish today. Okay? All right. We'll finish today. All right. Calculate the summation. This, our goal, calculate this summation. Then the trick is, the technique trick is, we double this formula, both sides. We double it. Okay? 2s equals, the right-hand side, we change the denominator. You double denominator, still power of 2, yeah, but the exponent is slightly different. Okay? All right. Then we compare these two formulas. You compare these two formulas. Then here, this red circle, you compare the corresponding terms. So these two terms, they have the same denominator. These terms, they have the same denominator, right? Then you do subtraction. Okay? Use the bottom formula, subtract the top one. Left-hand side, you get S, right? Left-hand side, you get S. Right-hand side, the first term, no subtraction. So you move down, inherit it. Okay? This circle, after subtraction, the numerator is 1. Numerator is 1. Denominator the same, 2 squared. Okay? Yeah. The next circle, the numerator also 1. Denominator 2 cubed. And so on. Okay? So you keep going forever. All the numerator is 1. All the denominator power of 2 with consecutive exponents. Right? Yeah. Then this is a geometric sequence, right? Geometric sequence. And its summation is 1. Summation is 1. Geometric sequence. Okay? Yeah. Can you see that? Geometric. How to calculate geometric sequence? Yeah. Let me give you the formula. How to calculate geometric sequence. Suppose you have a geometric sequence. The first term is A. Second term is A times R ratio, common ratio. Third one is AR squared, and so on, dot, dot, dot. Okay? But the ratio, common ratio should be less than 1. Okay? Yeah, should be less than 1. Greater than negative 1. Okay? Common ratio. Then equals A over 1 minus R. Okay? That's the formula. 1 minus R. That's how you calculate this infinite geometric sequence. Okay, infinite geometric sequence. Here the answer is 1. That's the constant. S is 1. S is 1. Then the remaining estimate. Yeah. So let's complete next time. Next time, we just have small amount of work. We can complete this quick sort, heap sort. Yeah. So we did most of the work. Then remaining about 10 minutes, we can complete everything. Question, Justin?
You have class on Tuesday.
No. Thanksgiving. Yeah, next week, whole week. Thanksgiving break. No class. Okay? No class. But I will post a document giving you hints for the homework assignment too. Okay? Yeah, I will post a document because in class I do not have time to talk about hints. So in Canvas, yeah, I will compile. Okay? Yeah. So I create a document, but I will add hints one by one. All right? Yeah. So then you study my document to help you answer relatively hard questions in homework assignment number 2. Yeah.
So the homework is still on, due on the 24th?
Yeah. Studio, 1 day grace period. All right. Yeah. Still give 1 day grace period. Yeah.